Okay, my wonderful friends, as you know, I have been doing a lot of light research, and I believe I have found the particles they are looking for at the colliders. However, we started with light, so we didn't have to go through the process of proton-proton collisions, huge mess of debris, and looking for the particles within that mess. We started with light, which is really the elementary particles, and we actually split those, so we could see them very easily. Now, Lawrence Livermore, I'm hoping will take an interest. I sent them all kinds of stuff to their Facebook page. They claim to be very interested in all the sciences. Now, this is the key where I found that a lot of the PhDs, they focus in on one little spot and then nothing else matters to them. And they don't understand that everything else does matter. Now, do they understand? I don't know. But I'm going to show you what they're saying, and then I'll show you what I can present, and then we'll see what their response is, and then we'll know if they're really that interested. Let's find out. Okay, I'm going to make a couple of claims. This is pulsed red laser, and it has a particle in here creating a field around the particle, which is very large, and that whole field has to move through the air with the particle inside of it, and that's it. Now, it's now beginning to accelerate, and the particle is literally pulling itself out of the wave due to a venturi, which is an accelerator, fully understood. Now we're actually seeing the particle, which is a photon. This whole area right here is a subatomic nuclear explosion. The particles break apart here. Normally they were attached together. Let me show you the evidence to support what I'm saying. That's an electron shower. These are sterile muons. This whole area here is irradiation from an explosion, and these are the waves of explosive, concussive reaction back here, backwards waves. You see them? They're not going towards the target. That's explosion backwards this way. This wave is going the way it should, towards the target. I hope you understand that. This is explosion backwards, and every pulse makes another wave. And all of these particles in the air are particles being excited by so much energetic reaction. This is fission, where the black broke apart from the white, and this is fusion, where it came back. There's no other way to look at it. This is raw white energy electron neutrinos, raw electron neutrinos. And we can focus them. They're not just going anywhere like splashing. This is exactly what they want to produce, is the separation from the muon and the electron neutrino, which are normally glued together, the black and the white particle. They want them to separate, and the muon goes sterile all by itself, and the electron turn into a shower. That is precisely what we did. This is what we have right here. There it is. When it came in, I showed you they were attached together. Right there, the black can't get through. Those black balls are the same size everywhere. They can't change size. Just like I'm showing here. They're too big to get through. They just can't get through. But they're also hard, and they slap that gooey white energy and shoot it right out the other side. What we need to do is put a receiver here somewhere. Now this is CERN. They're showing exactly the same thing I'm showing. The low energy particles coming in. These are the showers of electrons. All right, they come in low energy and they get high energy as they come up. Those are electron showers. The muons back off. Precisely what I've been showing you. The muons back out of here and the showers come through. All right, we need to harvest them right here. And we could do this inside of a little shoebox. You carry it around like a lunchbox. And inside of there, you could have thousands and thousands of these little lasers and receivers. And it looks like to me they are pumping out a hell of a lot of juice. When you see these electron showers, and they claim they can multiply it thousands of times. Now, I don't know if that's true or not, but here's what they claim. They're using proton-proton collisions. So they're using this, like this here. Boom, and they get all kinds of stuff. Well, then they got to make it turn finally after hadrons and on a axis and decay of hadrons, creating large flux, high-energy neutrinos. They created neutrinos and anti-neutrinos of all flavors, yes. So they have electrons and muons, yes. It's just like if we shot 10 different flavors of lasers in there, we'd get the same thing. I'm just using one flavor. So we're seeing electrons and muons, red, green, blue. The energy of the neutrinos interacting within the phaser goes from a few 100 billion electron volts to a few trillion electron volts. That is an increase of, they start out, you know, in the millions of electron volts, not in the billions even, I don't think. I don't know what they're doing exactly for their beginning energy, but normally photons and so forth, they're not up in these high energies whatsoever. So that is obviously an increase in energy, and we are seeing it in ours exactly like they're seeing it. We're seeing the neutrinos, and they are coming completely separated out, exactly what they want to see. Muons and electron showers. The blacks are the muons, electron showers. Now, this is a tragedy to not look into this. And our national colliders and so forth, you know, Fermilab, they're not going to do it because Don Lincoln refuses to even speak to me. So hopefully Lawrence Livermore won't take that approach. They'll at least examine this. I think I've shown some pretty good evidence to support my claims, even that light spins. There's light spinning around in a circle, around, 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 around. You know, all it's doing is coming down like this, spinning around. There's all kinds of them coming here. But the key is once they get through there, they want to separate. That's what creates the repulsion patterns. They're not interacting, flapping patterns. This is a single slit. We don't use a double slit. Single slit works just as good and better because we have a venturi. We can see it coming out the other side flawlessly. And we can see the Higgs fields. We can see them recombining and turning back into particles. Shown all of these things many, many times to the people that we are giving billions of dollars to do this research. They're not paying attention to this. That's exactly what they're showing. This isn't my pictures. This is our research. That's their pictures. That's what they're looking for. That's it right there. To be told I am a tinfoil hat guy by the guy that shows these particles as the most primary part 10 years ago. I said, Don, we found your particles. Nope. And that's Fermilab. Billions and billions and billions and billions and billions wasted. Not a pretty picture. So as far as I can determine, it's only a money grab now. And we want free energy. Don't you want free energy? I do. I'd love to be able to take something like this and go out and plug it into my car and drive around for forever. Never even have to stop. Something like this you put in your house and it runs your house, all the electricity in your house. I don't know how big it would have to be, but it wouldn't have to be hooked up to the grid. It would power itself. Once you power this. All right, hold on a second. I've got it. Here it is right here. All right. You got a laser. You need to shoot some kind of energy into that to make that laser fire. All right, so you put in whatever it is, 12 volts. Out comes either red, green, blue, whatever type of laser you have. Out it comes with the black particles, the muons attached to one of these flavors, and bam, it hits the venturi. It says, I can't get through there. The black ones, they say to each other, I can't get through this. I can't either. Well, what are you going to do? Well, just keep bashing that thing and see if we can get through. Well, you're never going to get through. The venturi isn't going to allow it. But what happens is this is literally a wave of almost like a paddle. Bam, bam, bam. And what squirts out there is nothing but white. Can I show that? Yes, I can. I will show you in a second that this is nothing more than like a push, and all the white goes in front of the black. Now, Here we have to harvest it, put it down through a photodiode or something so it can go down and can't come back out into a battery stack, run it through your whatever you want. And it should at least give us 200 times more than what we started. So if this took 5 watts to fire, we should get at least 1,000 watts out here. That's 200 times more than we started with. If that's the case, we got free energy. All right, so here's the laser coming through. I'm going to show you another shot, same laser, but a little different tuning on the Venturi. So the laser is shooting down here, accelerating like crazy. Everybody says you can't accelerate light. Yes, you can. It's very simple. If you can't see that, you got a problem. Then the concussion happens right here. And we see the black separate from the white. This particular case, there is absolutely no black coming through there. None. Zero. Zero. None. Zero. Now, you see the black sitting on top of the white? That's the only reason you can see it. There's black everywhere. There's black every single place out here, everywhere you can think of. But you can't see it because it doesn't absorb, it doesn't emit, it doesn't do anything. The only reason we can see it here is because it's sitting on top of the white, so it's obstructing the white from hitting us. And you can see the size of the balls. You see the same things over here. It's exactly what it is. Somehow they're sucking in all these black particles, and there is a discrepancy between the dark and the white particles. This solves that, because they say there's a discrepancy in it. It solves everything. It solves gravity, because the black wants to suck every white particle against it, and everything there is has white particles. That's what gravity does. It pulls it down. Now, this is the dark matter. The black is the dark matter. So that covers the dark matter. And where it is hiding has always been inside of the white matter. So you have the white matter out surrounding. Inside would be your black ball of the dark matter. Because the dark matter doesn't mind being on top of itself. And I think it might glue back to itself. And it might pull itself together. I'm just starting to think that's the case. At first I thought it didn't mind just being laying on top of each other, but I'm not sure, but I think now it actually attracts itself. But it doesn't mind being on top of itself. That I'm absolutely certain of. So what my configuration would be is this ball of particles would have a dark core like that of little balls, and they're all going to be the same size balls as those. All right? And all of those little balls would be inside, and you'd never see them. That's why dark matter you never see, because we only see atoms. You don't see down here. The only reason you see this is because we put a light and broke it apart. You never see that. Nobody's going to ever see that. And the things that they see at CERN, they just don't understand. The same thing with Fermilab. Absolutely no comprehension of what they're seeing. And as far as I can see, they don't care. It's got to be just looking for the money now, as far as I can determine. If this was done 10 years ago, just think where we'd be now. Okay, I'm going to show you something in a second, but these are the muon neutrinos, the black ball, which is this one here. And the electron neutrino turns into a shower, which is that right there. It's very hard to not understand this. It's exactly identical what they say, and the particles that we found, which are exactly identical to the ones that Fermilab and CERN find as the smallest particles, and they happen to make up light. But we were able to break them apart in the Venturi. So we created sterile muons and electron showers. That's pretty high-end stuff. And I presented it, like I say, to Fermilab, and Don Lincoln was not cordial at all. So there was no hope to work with him. I ended up going to the University of Geneva online through Coursera. I interacted with them. I showed them all this stuff. I told them what we're doing. We're using CMOS. And originally there was a little dispute about how that could happen and and it's impossible. Well, eventually I think I convinced them. I showed them. I said, you have to use CMOS. You can't invade that space. You have to sit out the side and wait for it to come to you. Otherwise, it gives you the observer effect. And that's what Don Lincoln was saying. The more closely you look at it, the more it changes. Well, no, you're putting some more energy into it to look at it. It's not changing by itself. It's not your eyeballs making it change. So anyway, they were actually quite nice at the end. And I said, can I work with you? Can we do something? And they said, no, we'll follow you on Facebook. And I said, well, okay. What are you going to do? So, and I wasn't paying, so I couldn't demand my money back. So anyway, at the end, so that ended there. And that was like 10 years ago. Now, the funny thing is, all the things that I mentioned to them about CMOS, they incorporated during their long shutdown. And focusing, I don't know, they did put focusing magnets in, but I told them about my Venturi, and I said how we did it, and I convinced them about the CMOS. They had to harden the CMOS so that it didn't get damaged from the collision. Again, we're working particles like this. They're working particles like this. When they hit, ours get hit like this. That's what they're designed to work for. They're not designed to get hit by that. That hits it, it's all over. And I said, because that's what they said. No, you can't do it. It'll destroy the CMOS. I said, well, not my CMOS, because I'm only using light. They were using bombs. So anyway, I hope you understand. It's just billions and billions and billions and billions of dollars wasted, and an opportunity missed that I don't know if it'll work or not, but I got a feeling it will. They're saying the same thing. Low energy showers coming through. For here, they're just coming through low, and then once they squirt it through the Venturi, whoosh, right up the curve. These are the electron showers. Low energy, high energy. Duh. These are the muons that never get through. They back off because they can't get through. Now, the only problem is they want to do things that are very, very convoluted. This is from the phaser, the thing they're doing. It's just too exotic. We did it right here, right on a bench. That's as much room as we need almost to do our job. And a couple of kids could do this with, a couple $1,000 and a couple little people, just a couple of little things, a few $1,000s. I'm not talking about billions of dollars like they use. And they've been doing it every year. It's just never going to end. It will never end. Ever, because they don't understand and they don't want to understand. That's my opinion right now. Now, what is Lawrence Livermore? They're also a national, agency. They're funded by us. We're paying their salary. Now, I would like to hear from them. Now, if I don't hear from them, it's a systemic problem. I know it's systemic because everybody I've contacted refuses to talk to me. When I present evidence, I don't present just theories. I present the evidence. I showed you what I can show that is what they want to see. They want to see the particles. I got them. I can even show you that red is not as powerful as green. See, the green reconcusses way out here. The red just gets pushed out of the way. That's the difference in the energy levels. I got so much to show that it's a tragedy that this has gone on for 10 years. And right now the planet is in so much trouble. I don't know what's going to happen here. But if we could have free energy, boy, I'll tell you, that would be the whole change of everything overnight. And this stuff is sitting on the shelves right now. It could be put together. I'm not going to do it. I can't do it. I don't have the resources. And the people we are paying to do the research that's supposed to get us this kind of energy have no interest, as far as I can tell. I hate to be critical like this, but boy, I'll tell you, I find it very hard to be any other way now. All right, I love you all. Thank you. Bye. All right, so why am I talking to Lawrence Livermore instead of CERN or Fermilab? Well, because I've talked to CERN and I've talked to Fermilab and nowhere. These are the smallest particles that they can find at these colliders. And this is what we found using light, which is light is basically the smallest elementary particle there is, only consists of a couple of muons and electron neutrinos. Now, this black with this fuzzy edge, that's what this is, exactly what they say, that's what they see. This glowy one can get big and small, and that's exactly what they say about this one. That one can never change size. This was 10 years ago. And anyway, so I didn't get anywhere with Fermilab, and I'm pointing that out very, very clearly, that they just didn't do their job. This was 10 years ago. I showed this. They showed these exact same particles in the collisions, and we actually make them separate. So I'm hoping that Lawrence Livermore will take an interest in this, because all we need is a shop bench to do our work. We don't need a 6-mile ring. So I did present this to Don Lincoln many, many years ago, almost 10. And he found these particles in 2013. And that's the dark matter, and that's the glowy energy part. They are combined together, called a Dirac neutrino. And when they hit our Venturi, they separate it. And he says exactly what I'm saying. This one, it's called a fixed particle, never exchanges. This one here can get big and get small. And it has really no weight to speak of. And it says exactly that in his summary. It says the fixed particle is the one with the fuzzy edge around it, the black one with the fuzzy edge. Never changes size. And the other one is just a glowy, it's a zero-sized particle. It can't be zero. It has to be something. And it has a field to it. So anyway, that one there has virtually no weight, almost none. But it must have something. But let's just go with none. So you got a big black one that's got all the weight, and you got one that has no weight. It has all the energy. And that's what happens. And my dipole electron flood theory solves this whole thing. Everything. Because you got black and white particles, but they don't realize that they thought the whole core was one proton for hydrogen, one proton, and then one tiny little electron out there. Absolutely not. It doesn't work that way. All these were dipoles, and this is what a hydrogen looks like. And there's approximately, I'm saying 1823, it could be 1839, I don't know. At one time I had an 1839, I don't know why I changed it to 1823, but it's somewhere up in that range of every one of these electrons has a certain weight. And I'm saying approximately 1823, dipoles make up one atomic mass unit, which is a proton. 1824 would make up a neutron. Now that's just an odd number. It could be close. It's in that range somewhere. A Millikan's oil drop experiment would have put it right around 1840. So it's anywhere. I would go between 1823 and 1840. But that's how many particles are in one proton. So when they smash them together, they just get bits and pieces and chunks all over the place. So here's what happens when they smash them together. They get these kind of particles right there. Right? They think they're just hitting two solid things together, and they're getting little pieces and bits. They're really not. They're hitting two stable balls of matter. And they hit head on, or some close to head on, and then they just splash all over the place. Now, some of them come out one tiny little bit, yes. Some of them come out 2, some of them come out 10, some of them come out like an X particle, a million. So they got a zoo. But look at this particle right here. You see that particle? That's a photon. This is one of the colored neutrinos, and they got the red, blue, and the green, just like us. And they see photons of different energy levels, but it's just debris to them. To us, we started with these, and then we broke them up to see these and the black. Now don't forget, every particle has a big field around it. So what they're doing is they're hitting field to field. And they don't realize that they're crushing fields to fields. Sometimes they don't hit exactly head on. Hit exactly head on, they get an explosion of every little particle, yes. But most of them hit like bang on the edge, because they try to skirt off each other. They send like 25 billion particles at a time, and they're lucky to have 25 of them hit, because they try to get the fields bounce off. They're like rubber balls, boing, boing, and sometimes they just can't. They go, oh, boom, and they go all over it, and that's what you get here. But sometimes it's just off the edge, and they get big blobs of stuff all over the place. They cannot control it. We control ours by literally forcing the fields into a confinement that they can't get away from, and slapping them through it with the dark matter. All right, don't forget, all photons start out the same way. I don't care what color they are, blue, green, red, we saw them all. And they're the same color. I mean, the same configuration, different colors. The black is different though. The black is the same in all of them, and it is a solid. It's the same size, and it is solid, and it is slapping that white out of here with a vengeance. And we can focus this, as you can see. We could create, there's all kinds of creative ways we can do this. I have some other designs now for the Venturi, but this was pretty effective. That completely separated the black from the white. That's fission. When it separates, and when they come back together, it's fusion. Now, when they do it in the big colliders, they're using big particles like this. And they're trying to make them break and then come back to create energy. To make them break, you have to use just as much energy as to when they come back together. I don't see ever being able to have fusion work. Plus, the sun doesn't work on fusion anyway. They talk about the sun working on fusion. They think it just crushes itself into releasing all this energy. No. It could. Let's just take the example of the sun. The sun itself on the surface is 10,000 degrees. Now, if fusion was the case, it would heat up from out here and then dissipate as it went out and went out and went out. It does not. It's fusion down here, let's say. Let's say it is. I don't care. So it's fusion, and it gives off all kinds of heat. Heat dissipates with distance. The sun, as it gets out further, gets to be millions of degrees. Here it's 10,000. How did it get to be millions out here? They can't explain this. They want to spend billions of dollars to try to figure it out. I can tell you exactly why. The sun is a gigantic attractor of particles, and there's so much attraction that as it spins through the universe, it's got so much density to it that it illuminates. It illuminates and sends out all these rays. That's the stuff that's coming off the sun. And as it goes out, it scrubs where it has to plow through. Just like the particles I showed you glowing, and I'll show you again. Let me show you what I'm talking about, why the corona is so hot and the sun's surface is only 10,000 degrees. If it was 10,000 degrees out there, you would expect it to be 5,000 out there and 4,000 and 2,000 and so forth as it goes out. Not the case. 10,000 here, millions out here. And the reason is the sun is spinning and scrubbing through the universe with all, this is dense with particles, and it scrubs through, and it creates this negative zone out here, which is exactly like our zone. It's called the ionosphere. And that's what we have, the same thing. And guess what? Our planet is 100 degrees on the surface, approximately, a little more now probably. Out here, take a guess how hot it is out there. It's almost 3,000 degrees. Nobody ever talks about that. Why is it 3,000 out here? And then guess what? As it comes down, before it hits the earth, it goes down to minus 100 Fahrenheit. How could it be really hot out here and then really cold right there and then hot back on the earth? I can explain it to you. Everything is a dipole. Everything has a positive and a negative. The positive side is, if you want to call it, the dark matter. And the negative side is the glowy matter. And that glowy matter is scrubbing everybody else's glowy matter. So you end up with a zone called the ionosphere, which is hot. All right, my statement is that the Earth down here is spinning and being pulled around the sun and being ripped along the arm of the Milky Way. There's a lot of interaction on the atmosphere, which is way out here. The atmosphere comes way up here. All right, so let's start where the atmosphere ends. This up here is way out at the top. There's almost no atmosphere out there, but there still is. There's no empty space. None, zero. Here, though, we got the scrub. This is the ionosphere. This layer right here, where it scrubs and meets space and rips against the space, this is where you got this interaction where these nothing but negative particles. In this layer, the northern lights is where you see these negative glows because they're nothing but electrons. It's high temperature of 1,500 degrees Celsius It destroys meteorites, and it can damage missiles and these orbiters and so forth. They have to have special shielding and all kinds of stuff. Now, but here, 1,500 degrees Celsius, that's 2,700 or so degrees Fahrenheit. Right below it, right, there's another layer right here, all right, which turns extremely cold. Minus 80 degrees Celsius, that's 112 negative. So you go from 2,700 above zero to 100 and something below zero. Right on this border. That's because this is a dipole. That's the white glowy part, and that's the black part. Now, what happens down here? You get ice. You get these, all kinds of hail, and this is the interaction with the lower atmosphere below. And you get all kinds of hail because it's minus 80 degrees. And the more compression you get, the more condensation, the bigger the hail gets. We are getting compressed like crazy because of all the gases going into the atmosphere, crushing. It's going out more and more and more. And that's just going to be more and more go out this way, scrubbing harder and harder. This is not empty out here. This is just, no matter where you go, it's going to have the same density of particles out here. They're going into this. We're going into this. All right, the more we burn, so we might be here. Tomorrow I might be here. Tomorrow, the next day it's just inflating our atmosphere. And that is causing a lot of turmoil and a lot of problems with airplanes hitting pockets. And there's a lot of compression here now. And it's going to get worse and worse and worse. The more we burn, the more it does. And the last stage of this electrons infiltrating our space is they get absorbed by the Earth. And the Earth, of course, is getting warmer. That's just the way it works. It's flowing through in phases, boom, 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 into the Earth. Dipole flood theory solves the whole thing. It's very, very simple to understand. I never in my life realized that you could separate the negatives from the positives in dipoles. I knew about dipoles. That was my theory forever. But I thought they were stuck together and you could not disassemble them. I was wrong. You can disassemble them, as I showed you. This is the key to the whole thing. They see these particles, but don't really understand where they came from because they're in a field of debris. We started with light, so we started with those particles. Then they were able to split apart using a Venturi. A Venturi accelerates water, it accelerates gases, accelerates everything, and light is nothing more than atomic vapor. Okay? The same as like water vapor. It literally is the same. But it's only made out of these two particles, back to back, and that's a photon. Now, again, we separated them and broke the black away from the white. This is what we need to charge your cars and to drive and make energy and electricity. And here it is, sitting all by itself. I can't see why we can't harvest it. This is exactly what they've been trying to do. And we did it. Why is this not looked at? Well, I know why it's not looked at. Because of the guy that runs this place here, Don Lincoln, Fermilab. He absolutely refuses. I contacted him 10 years ago. I said, Don, we found your particles. Can we talk? Nope. I said, well, how can you explain this? Nope. I don't want to talk to you. And I kept asking him questions, even like the corona of the sun. Can you explain that? Can you explain heat? Can you explain why heat has weight? Can you explain all these little details that they overlook? And can you explain how that's not acceleration? Can you explain how we found these particles are identical to the particles you have, and these particles here, which are identical to the ones that you show in your collisions? We've broken the little bits and pieces off the two, same as you did, only we did it by using the smallest particles to start with, right here, and sending them down. And the green does the same thing. I just showed you, let me show you the particles. Here's the green. That's the same particle, all right? It's got the two white spots and the two black, but it's green, and that's the radiation it gives off is green. The red gives off red. Now, and it's the same particle, the same construction, a different spin. This does not spin as fast as the green, and it is spinning. It's spinning like this, coming down this way. And the only one that's showing up is the one that's exactly in line with the Venturi. The other, they're all over here. They're everywhere. You just can't see them. And I can prove that by showing when they do explode, they show up here. You see, here they are. Here they're here, coming this way. You just never saw them. This one you can see only because it's being accelerated towards the target. These are being pushed back against it. Look at the glow here. This is only accelerating somewhat. This is being slammed back against, like, you know, like a freight train. Look at the glow. And you don't even see them here. It's like it's missing here. All of a sudden it's here. Why? The only reason is because it's being concussed backwards. And the reverse EMF, reverse electromotive force, is extremely strong. And you can see it back there, way, way, way out at the back. You see how strong those particle reverse waves are? Way, way, way away from the source, which is down here, where the nuclear explosion happened. And that is a subatomic nuclear explosion. They're not fully atoms, they're particles, but they are fission and fusion, and they're exploding. You explain it some other way. I'd like to hear how. Okay, this is Lawrence Livermore National Laboratories, and this is their what-if statement. And they're saying, at Lawrence Livermore, the realm of what's possible is only bounded by the questions we're willing to ask. Are you willing to ask the questions and then answer them honestly? Our multidisciplinary teams, they know a lot of things about a lot of things, and that is absolutely essential. Multidisciplinary teams fearlessly, relentlessly pursue big ideas using innovative science, that's my stuff, and technology to meet our national security mission to make the world a better place. That's exactly what I'm trying to do. And I can show evidence of my research, not just theoretical. I have the evidence that I would want them to examine. Now here's their statements, and here's their little video. It's a couple of minutes long, that's all. And then we're going to go into my evidence that I would like them to pursue. This is Lawrence Livermore. This is an introduction to what they do and how they feel about research. Here it goes.
Starts with two words. What if? It's the question that brought us all here. What if we could ensure that the nuclear weapons in our stockpile are safe, secure, and effective without setting one off? We'd do that. What if we had a computer capable of more than 2 quintillion calculations? Yeah, that's a real number. In the time it takes to say, 1 Mississippi. We have that. What if we could create a machine that builds specialized materials in different shapes? We built that. What if we could harness fusion, the process that drives the sun, in a lab setting to support national security and take important steps toward a clean energy future? We can, and we did. At Lawrence Livermore, we turn big ideas into reality. We protect our nation. We make the world a better place. We believe curiosity spurs innovation, and innovation turns into impact. In fact, our research on powerful lasers helped enable the newest tiny chips that let you watch this on a handheld device. Color-coding human DNA so we can identify mutations causing diseases like cancer. Combining AI with some of the most powerful supercomputers to find new therapeutics. Creating a first-of-its-kind climate research center to better understand the world around us so future generations can, too. When faced with the world's most complex problems, our diverse teams and partnerships make the impossible possible. And for us, impossible is just the beginning. We shape the future by anticipating new challenges. Because our what-ifs lead to what's next.
Okay, I'd like to be part of that.